Hey everybody, welcome back. It's another episode of Everything is a Spring. Derek, how are you, buddy?
Hey, Jim. Good afternoon. I'm excited to podcast. How's your week been, man?
It's been good. It's been like really weird because the first half of this week I was actually in Royston, Georgia. I was learning a CNC machine that we're going to be bringing down here. And so that kind of threw my whole week out of whack.
I bet. I
Just
remember you
because
talking about it a little bit last week, too.
Yeah. So it turned out good. I think I've got a pretty good handle on it. It's very similar, really, to the other CNC machines that I've run. This one's it's a CNC mill as opposed to like a router. But functionally, like they're very similar. All the principles are the same. It's just the software is a little bit different and the user interface is a little bit different. So it's just getting used to that. But
Yeah, get your little
otherwise,
subject
good.
matter expert, Mr. Fix It.
Mr. Fix It. Yeah, it was actually really fun. So Monday I got up there and we were trying to run some programs, but the machine actually broke. Which would maybe sound like a bad thing, but it actually was good because I got to pull the machine apart and see what was under the hood. And
Oh, I guess
it
better
was
than when
pretty,
you're in production, right? Get a little
yeah,
freebie.
absolutely. Yeah, we were able to fix it really quite easily. It took us maybe a couple hours. And part of that was just running to go get the part, which we managed to get from a local hardware store. So it was pretty cool. It's a Fadal machine, so it's basically Fadal is like I guess it's one of the more accessible like CNC brands. I'm not sure if that's the best way to put it, but the machines are usually a little bit less heavy duty than some other machines, but they're also a lot cheaper, a lot easier to work on, a lot easier to fix.
Oh, is this the
Um,
Ryobi of CNC machines?
Yeah, I guess so. Maybe like a little step up. Maybe it's like the rigid of CNC
Ooh.
machines. Because like the Ryobi, I would say is really kind of your hobby grade stuff. And this is really, I mean, this is an industrial commercial grade CNC machine. It's just on the lighter duty end. But what we'll be using it for is primarily aluminum. So for that, this is going to be perfect. But you really wouldn't. So aluminum is like a very soft metal, right? As opposed to like steels or stainless steel or titanium or Inconel, which are very high performance alloys, but are really, really hard to machine, are really tough on the tools, are really tough on the machines. And there are actually companies that they basically view their CNC machines as disposable
Really?
because basically, yeah. I mean, because what they're doing is they're machining stainless steel parts. And the way that you basically make money in the CNC machining world is you machine as fast as possible. And there are companies, like especially for aerospace or defense contracting or whatever, that will pay a premium for fast turnaround. And so basically to expedite, you have an expedition fee, right? So if you want your parts really quickly, you pay more for them. And companies will actually use that fee to basically pay for the new machine. So they're basically like overclocking the CNC machine, but they're making enough money on it to pay for the machine. So
Perfect. So, like, if it
by the
burns out,
time yeah, you just buy another one, which to me is crazy because you're talking about $250,000 machines.
sheesh.
But basically, yeah, I mean you'll run them hard for like 2 years, 3 years, and then you'll get another one, and the old one goes basically to scrap
Hmm.
because it's just clapped out. But
Just pull some parts off it, call it a day.
yeah, basically, yeah, you sell it to a secondhand or a parts retailer or whatever. Basically, they'll just pull it apart for scrap because the tables, the ways, and all are so worn out. It's just from the company's perspective, like it just doesn't make sense. It's not worth it to fix the machine because you just buy a new one and you keep going.
Gotcha. So, yeah, that's
So you
interesting.
sell it off to somebody else. Maybe they'll fix it. Maybe they'll pull it apart for parts. Maybe they'll scrap it.
The long and short of it is
Just
it's not
depends.
their problem anymore.
Exactly. And then they avoid the downtime.
True.
But yeah. So anyway, so that was kind of interesting. But then it threw off my entire week. And then I had to scramble Wednesday to kind of get things back in line, and then really even Thursday and Friday I've just been moving. But Saturday I got to work on the Mustang a little bit, which was fun, and
Nice.
take a little bit of time. But yeah, so it was good. Yeah, pretty good week.
Right
Pretty good
on.
week. What about you? What you been up to?
Man, this has been one of the easier weeks I've had. My great aunt came over yesterday to give me a little break from caretaking. So, I went out, ate way too much sushi, just enjoyed myself, little treat yourself
Nice.
day. And
Heck
then
yeah,
I'm
man.
getting some drinks with some friends later today, so should be good.
Sweet.
Actually getting out of the house, and work was surprisingly cordial. Like everything worked out. Things are getting, for right before the holidays, it's a little suspicious. It's just like, everything's all falling together.
What's gonna go sideways next?
Right, but it was a good
Yep.
week, so I can't complain. I take every good one I can get.
That's good. That's good. Heck yeah, man. Oh boy. Yeah, we are closing in on the Christmas season. Do you have all your Christmas shopping out of the way?
Most of it. Like all my family has their presents wrapped and ready. I'm trying to, well, one, I spent a lot of money on the trip for next year, so I'm really trying to budget out the rest of the year, and I'm really focusing on stuff we need. I know that's not very exciting, but, I've been doing a lot of work on this house. Like finally got, security back up and operational. Everything's back up to spec. So now we can get towards some of the more fun things. But yeah, I'll probably end up doing some last minute Christmas shopping. But everyone that would get mad about not a present has gotten theirs.
Oh, that's good. That's good. I am awful about Christmas presents. I'm just terrible about it because I really want to I want to make something or get something at least that's pretty personable. This is actually something they're gonna want. But that's very tough to find sometimes.
Yeah,
so.
Or time consuming because you're a great builder, but
it's true.
You have a whole job and another job.
Oh my gosh!
Speaking of Christmas presents, have you gotten a package in the mail?
I have not. I've looked for it. But
Look
I have
for
not
Santa soon.
Okay, sounds good. I appreciate it. We'll get something. I'm so excited. But yeah. So I guess I don't know. Do we have anything else to talk about right now? Or
I'm good to jump right in. I think that's a pretty good time.
All right, Derek. How far west have you been? Have you traveled very far in the west coast of America?
I guess the farthest I've been is California, but it was really just a rock and a skip. I didn't get to actually enjoy it. I was in an airport for 5 hours, give or take.
Yeah. Okay. How was the farthest west you've been where you've actually stayed there for a little while? You actually gotten out of the airport?
Trying to remember the map of the United States. I'm guessing Utah is more west than Colorado, right?
I think they're pretty even.
Yeah, I think Utah, Wyoming, that area.
Okay. What were you doing up there?
Oh, hitting up some national parks a couple years ago with my roommate. We just flew out to Denver, rented what we thought was going to be a really crappy car, but the rental car place only had this big old SUV, so we were pimping out. And I just went and hit as many national parks as we could, camping in the car when we wanted to. A couple days late in the trip, we got tired of that, so we would rent a lodge or something just for a day and get back on the road. But that's the last vacation I've been on, so it's a core memory.
Okay, yeah. So Utah is directly west of Colorado. So,
right, so probably Utah as far as adventuring.
So you've actually been further west than I have.
Where you been?
The farthest west I've been is Colorado.
Oh, we got to change that.
Yeah, I would love to. I would really love to go out to southern Utah kind of area. I think that'd be a lot of fun. But also, one of the places I've never been that I would love to go is the north, the Pacific Northwest. Right?
Oh,
it's so beautiful.
If I could get the money to rent a sports car and drive from Portland down to San Diego or something, that would be insane.
That'd be cool. That'd be pretty cool. But yeah, I mean, it's just so otherworldly, right? Because it's this really, really wet rainforest type thing, but it's cold.
Yeah.
Right. And there's the salmon runs and all this. Ooh. It's just beautiful, right? Well, Derek, our episode this week takes us to a particular part of the Pacific Northwest, near Tacoma, Washington.
Oh, that's where trucks come from, right?
There is a Toyota Tacoma. I guess that is probably... Well, okay, so American car manufacturers, or I guess just car manufacturers that sell into the American market, they kind of have a habit of naming their vehicles with, according to different passes or
the
whatever.
2024 right? GMC Sierra.
Yeah, there's the Sierra, there's the Durango.
The Ridgeline.
the Ridge Line. Yeah, there's the Tacoma, obviously.
Bronco.
There's but the Bronco's not really named after like a geological feature, right?
Oh, I thought it was a city, right?
Um,
Or is that a
is it?
Bronco's a
I
horse?
think it's a horse.
I'm
Yeah, yeah,
stupid.
yeah. Because it's no worries. Well, I actually think it would be really good for like Ford to. Okay, hear me out.
All right. Ford,
All of our Ford
take some notes.
engineers listening. I think that they missed a golden opportunity in terms of like their horse naming convention
Mm-hmm.
to name, because like they've got like the Ford Raptor or whatever, and like okay, that's
I guess
cool,
a
right?
dinosaur, fine.
But like where hear me out, Derek.
I'm hearing
Like
you.
where's like the Ford I'm also hold on. I got to look up the name of the horses. Horse breeds.
Yeah, listen up, Ford Engineering and Marketing. We got a lesson for your ass.
Like where's the Ford Thoroughbred?
You
Like
know?
am I wrong?
That I feel like that would be a really good heavy duty.
Yeah, or like where's the Clydesdale?
Ooh, Clydesdale. That sounds like a sports car to me.
Like that's all I'm saying, right? So Clydesdales are like these like super strong like draft horses, like heavy draft horses. So they just can pull and pull and pull. So I'm like, why is it not the Ford? Why is it the Ford F-150 when it could be the Ford Clydesdale?
True. And you know what? Ford, you can send our check in the mail for that one.
Yeah, free. Hey, yeah.
I won't say
I'm gonna
free.
be
Send that check in the
not
mail.
free. Yeah, I'm gonna be charging $100,000 for that name.
Easy. Just for the name.
Easy.
Just for the
Just
name.
for the name. Just for the name. Derek, really, we need to go ahead and start our own truck company so that we can go ahead and claim that name so that when Ford comes to buy it from us, we have some legal precedent.
Dude, I bet me and you give us like 4 years for me to like learn engineering for one of those years. I bet we could put together a hell of a truck. Like one that's not one of those modern trucks where it's just like the cab's the size of a car. I'm talking about a truck for people that actually haul. You know what I'm saying?
Yeah.
Folks that
A
actually
working
work.
man's truck.
Yeah, get back to our basics. 2 people in the cab, 3 in the middle, but you got some space back there. You got if I want to tow a semi truck, I can do
it. Absolutely. Anyway, we're getting off topic. So, the particular part of this is actually very close to Seattle, right? So this is just south of Seattle. And what we're talking about today is the Tacoma Narrows Bridge. And the Tacoma Narrows Bridge, when it was built in, I believe it's 1940. Yeah, so it's the third largest suspension bridge in the world at the time, behind the Golden Gate Bridge and the George Washington Bridge. This is a massive architectural and civil engineering undertaking. And of course, what else is happening in the late 1930s and early 1940s?
I can't think of anything. I
don't think there was really
cool, right?
else.
Everything was just really chill and no one was trying to take over the world, right?
Yep, everything was super chill everywhere in the world except for a small conflict, really a paltry conflict in the Europes and in the Asian theaters. So World War II is happening right now, or is about to happen from the United States perspective. So that adds in kind of a little bit more of a political element, which comes into play. So this bridge, the Tacoma Narrows Bridge, basically it connects the state of Washington, and there's this thing called the Kitsap Peninsula, which is basically it's in the, I guess you'd call it a bay. That Seattle, yeah, I guess it's a bay, but it's kind of a weird shaped bay. So if you look at a map of Seattle, basically the harbors or whatever are like really fractal kind of. So there's lots of little peninsulas and islands and stuff. And this particular peninsula, the Kitsap Peninsula in particular, is like this really large bit of land, but it's only connected by this tiny little piece, actually on the west side of the peninsula. So it's really inconvenient. So they decided, hey, we're going to make a bridge here to connect, this peninsula a little bit more, so we can get more traffic onto it.
Good old bridge of necessity. Love those.
Yeah, and so it crosses the Tacoma Straits, is what it's called. And they decide this is going to be basically the government puts out like a kind of a call for design. Basically, this is kind of how government projects go a lot of the time in the United States, is the government will say, this is what we want to do, and then they'll kick it off to the private sector to basically say, hey, what can y'all come up with? And then the private sector will then make bids on the project, and basically the government will choose whichever one they think is best, which normally, Derek, what do you think that would be?
The one I think it's best.
How does the government define the best?
Uh, I'm not. I mean, not big government person. The cheapest.
That's correct, Derek. So basically, price is a huge factor in this. People have been talking about putting a bridge at this location actually for a long time, going all the way back to like 1889. The Northern Pacific Railway had talked about putting a rail bridge across, but nobody really did it seriously until about the 1920s. And that's when the Tacoma Chamber of Commerce really starts pushing like, hey, this would be a really good, benefit to the local economy and, all this kind of stuff. And so they really start pushing to have a bridge construction seriously considered and implemented. So they actually end up getting a couple people to consult, including Joseph Strauss, who goes on to engineer the Golden Gate Bridge.
Oh, that's awesome.
And yeah, it's good. So they basically have a meeting, and they have a preliminary proposal in 1929, but the chambers, no, that's not really going to work because the money isn't coming in properly. And so basically this can get kicked down the road a few more years. And finally, by 1938, they had found a way to kind of make it happen. And what they had come up with is basically that the state of Washington in 1937 creates the Washington State Toll Bridge Authority. And so the idea is basically that the bridge is going to be made and then it's going to be a toll bridge. So the tolls are going to help cover some of the cost and then be an ongoing revenue for the state.
All right. I was about to say, I was like, you couldn't let it be free for a little while, but I guess they do have to, make the ones meet the zeros and all. That's fine. Mm-hmm. I'll pay to go across the bridge.
Exactly. And prior to this bridge, the only way to get across here is a ferry. There's a ferry running that is going back and forth across the strait. But eventually they kind of get everything together. There's some pressure from the United States Navy, who also wants this bridge for various reasons.
Oh, okay.
And they come up with there's a Washington State engineer by the name of Clark Eldridge, and he produces just a very tried and true, cut dry. Here's a suspension bridge that will work. Nothing fancy about it, but here you go.
All right, keeping it simple.
And so he requests $11 million
in those monies or today's monies?
In those days' monies.
Oh, Lord.
Which is the equivalent of $212 million in today's money. And he requests that from the Federal Public Works Administration. So that's a lot of money.
Mm-hmm. I guess it is a big bridge, though.
It is a big bridge, right? It's the third largest suspension bridge in the world at the time. And one of the really crucial things about his design, well, let's talk quickly about the other design that comes in first. So there is there's another group of engineers that come up with a second design, and it's from the Reconstruction Finance Corporation, which is basically, it's an East Coast-based engineering firm that offers a new solution. What they have come up with is that basically there is, at this point, the effects of wind on suspension bridges is pretty well known. And so there's a lot of care taken to mitigate those stresses. So like we talked about last week in the Angers Bridge episode, the aerodynamic forces were actually causing the bridge to sway quite a lot, even before the soldiers marched onto the bridge. So there is this understanding of like environmental forces and wind load and stuff like this. having a huge, potentially catastrophic impact on suspension bridges. That is understood at the time. So there's a paper that's published fairly relatively recently to the time period that we're talking about, and they're basically what they are talking about is basically a way to take the wind load and transfer it away from the main span of the bridge and transmit it through the cables to the main, like the uprights, the columns, right?
All right. So like you want to take the force from the stringy bit to the hard bit and make sure, that makes more sense. Sure.
Right. And so this paper shows that the stiffness of the main cables, so if you have really nice, thick, stiff main cables, it's actually going to absorb like half of the static wind pressure and wind loading. And it's going to then transmit that force into the anchorages and towers. So basically what that means is you can have a much narrower, much shallower bridge, which means it's going to be a lot cheaper to produce.
Okay, that's good.
Yeah, so basically what ends up happening is this guy, Moisef, I think that's how you pronounce his name, Moisef, I don't know. I'm going to go with Moisef. Moisef proposes to do an 8-foot plate girder bridge. So basically, it's just a 8-foot tall thing, and that's what's kind of creating the structure. The original proposal from Eltridge calls for a 25-foot deep truss bridge to act as the main causeway of the suspension bridge.
That's a huge difference. Can you put a train on 8 feet?
Enormous difference. So this is not for trains. So this bridge proposed is actually for just car traffic.
Gotcha.
Yeah. So not for trains, but that is still a enormous difference, right?
Oh, yeah.
So I mean, so let's get into the engineering just a little bit, and we'll just kind of simplify it a little bit for the sake of
me being
just for the
dumb.
sake of simplicity. well, just to get not too into the weeds. So, Derek, there's a couple different factors that play into stiffness.
Hey,
what do you think might have an effect on the stiffness of a beam?
I'd say the length, right?
That's right.
The material.
Yep, that's also true.
And probably, obviously, the thickness, right? Like the diameter.
Yes. So right now we're really talking about, I guess, really like a rectangular beam because we're talking about bridge. But if you were talking about a circular, then yes, that is also true.
But it's the width then.
Yeah. So if you look at a beam that is, I guess, you've got two. So if you're looking at a rectangular beam, you have two primary dimensions. Because one of the things that we do in engineering quite frequently is we actually break down, so like the whole, basically what we're saying is that, yes, the beam, let's say the beam is 12 feet long. And so if you have a certain amount of force over that beam in a certain cross-sectional area, that's going to be basically what that will give you is like the deflection of the beam. So obviously if you have a longer beam, all else held equal, you're going to have a greater deflection.
Makes sense.
Yeah. So one of the things, though, that can be kind of challenging about approaching design that way is that you have to iterate like a lot. So one of the ways that engineers kind of get around this is to basically create kind of this idea of a like deflection per unit length, or we'll talk about like stiffness per unit length. So we'll just talk about the cross section of a beam.
Oh,
and then
so
that'll
they
give us
split
the
it into
stiffness.
reasonable chunks for the calculation?
Yeah, so basically what we do is like for our beam, we break it down into just a cross-sectional area of the beam. And then from that, we can get the stiffness. Or in this case, if we're talking about bending, you're actually going to be talking about the moment of the beam. And then from that, you can calculate the total deflection of the beam depending on how long it is and all this stuff. And it basically just lets you very quickly and easily iterate the design to say, okay, well, we need to have the bridge or the beam supported this far apart to be within our total deflection that we can allow.
Oh, so you like take the material like this beam and you're cutting it for all intents and purposes, into slices and doing the calculation slice by slice, so you can
Yeah,
multiply it.
so absolutely, and you can also do this. Yeah, absolutely. That's exactly what you were talking about. And what that allows us to do is basically just create a simplified tool, I guess, to start with. And then at the end of it, you still would want to go through and run your, basically check your calculations and make sure everything holds up. But for the sake of our purposes here, yeah, that'll suffice. So basically, for a rectangular beam loaded in a vertical direction, there's two primary dimensions. There's the height and the width, right? So both of those dimensions contribute to the stiffness of the rectangular cross section. Derek, what do you think, like which dimension, I guess, do you think creates more resistance to bending?
I guess in this situation, your y-axis, like up and down, since it's
That's
a
right.
longer object.
Yeah. So the height of the beam actually has a cubed effect on the stiffness of that beam.
Really?
Right. Absolutely.
That's way more than I thought it'd be.
Yeah. So, and basically what we would say then is you're not actually, so if you take that 8-foot thick truss and you make it a 25-foot truss, 25-foot high truss, you're not actually increasing, right? Because that's basically a 3 times. You basically have increased that height by 3.
Right. That's
Right.
a lot of weight.
That's a lot of weight, and it's also a lot of material. But you're not actually increasing the stiffness of that beam by 3 times. You're increasing the stiffness of that beam by 9 times because it's 3 cubed. So basically, this second design from Moissif is 9 times less rigid than the original design.
That is wild to think about, even though it seems like just thinking about, oh, it's shorter. Surely it should be more structurally sound. That's interesting.
Yeah. So, so it might be structurally sound, but in this case, which is the critical part of it, it is much, much less rigid. And so that is going to become a problem, as we'll see here in a moment.
Surprise tool that'll help us later.
Exactly. But basically, because there's so much less material, it's a lot cheaper to build. In fact, the bridge ends up getting built for only $6.4 million.
Oh, you're telling me they didn't go with old tried and true?
They did not go with old tried and true because
government just puts government glasses on. Well, it's military grade. Surely it must be better. Nah, that just means it's the lowest bidder, bro.
Yeah. So basically, this design wins out because it's priced at like half the price of the other one. And
then you can fill your pockets as the government.
Yeah, it's true. Yeah, I don't know how rampant corruption was in the 1930s, but
I'm gonna guess ain't nothing changed.
Ain't nothing changed. Yeah, that's my guess. So the construction begins on the September the 27th, 1938, and it only takes 19 months for them to build the bridge.
You're kidding?
Yeah, which is actually really fast.
You can build a bridge in 2 years or less than 2 years.
Yeah, just under 2 years. So, quite incredible. And the main span is 2,800 feet long.
Dang.
Making it the third largest suspension bridge in the world, following the George Washington Bridge in New Jersey and New York City, and the Golden Gate Bridge connecting San Francisco and Marin County.
I guess when you ignore OSHA, you can slap that bad boy together real quick. Everyone just ride the beam all the way up. We're gonna start smacking stuff with a hammer and don't fall.
Just don't fall. There you go. Yeah, back when men were men, we died like real people.
Yeah, at 9.81.
But one of the other things, the bridge planners really didn't expect like a huge volume of traffic. So the bridge is also only 2 lanes wide.
Oh, no turnoffs, no shoulders?
No turnoffs, no shoulders, which means the bridge is only 39 feet wide.
Yeah, so just don't crash. There you go. Easy.
There you go. There you go. So, Derek, we've just talked a little bit about, aerodynamic loading, and we've just talked a little bit about beam stiffness. So, what then would be the benefit to having a wider bridge?
Well, a wider bridge, for one, traffic safety, obviously. But a wider bridge, it seems like there would be more material to deflect aerodynamic forces instead of just having this much thinner thing that's going to easily sway. Because even though it's much heavier, that helps you in this situation because you have, the same amount of wind going against a heavier structure going to be much more stable, all things considered, compared to like everyone who's gone hiking has gone over one of those rope bridges, for example.
Yeah.
The wind blows on that thing, you're going to feel it.
You're going to feel it. Absolutely. Well, the same is true for the Tacoma Narrows Bridge of 1940. When the wind's blowing, you're going to feel it.
Oh, no.
And because the bridge was so shallow, only 8 foot deep, and relatively narrow, only 39 feet wide, the wind, which in this area of the country is quite severe, quite regularly, the wind is causing the bridge to oscillate back and forth, in some cases like 4 to 5 feet in the center. And so the workers, and this is still happening, like this is during the bridge's construction, the workers are on the bridge, building the bridge, and they're feeling the bridge moving up and down 4 to 5 feet over a 4 to 5 second interval, and they name it Galloping Gertie.
So instead of acknowledging the problem, they're like us today. We're just going to meme it.
Yeah, absolutely. So the workers start calling the bridge Galloping Gertie, and the public picks it up, and the name sticks.
Galloping Gertie. That's what I want to climb across.
Exactly. So, and in fairness to the project construction people, they do notice the considerable oscillations that the bridge has, and they do take a couple different options to try to mitigate it.
All right.
So what are some ways you think that you could mitigate the oscillating factors? Because keep in mind, primarily it's going up and down, but it is also moving side to side a little bit.
Right, it's going up and down. I don't know much about engineering, as previously shown in all these episodes, but if it's not too much material, could you make something that supports the suspension cable a little bit more, like more points of contact maybe? Alternatively, I don't know if we were thinking like this in the 30s, but maybe add some material to the sides that doesn't necessarily change the structure, but deflects the wind intentionally, like off to the sides or something.
Now that is a very interesting idea, which they did not try. But that is that is something that future bridges do employ. So a lot of suspension bridges now are actually designed with specific aerodynamic structures incorporated into the bridge to prevent wind oscillation. So that is actually a really good idea. But aerodynamics was really not very advanced at the time, so they did not try that.
That's fair. Hey, but if I could transplant myself in the 30s and not get hit by racist America, I'd be a great engineer.
That's very true. Okay, so they try a couple things to... they do try some aerodynamic things. I'm sorry. We'll get into that. So they try a couple things. First, they try to attach a bunch of tie-downs, basically, to the bridge, and then with big steel cables, anchor it to shore with they have 50-ton concrete blocks.
Oh, they just freaking slap some rope on that bad boy and...
Pretty much. They're like, well, let's just tie it down so it can't move anywhere.
Hey, that's what I do to my tent. Surely it'll work.
That's exactly right. Well, unfortunately, the cables snap, and they don't do it again. So that didn't work.
At least they tried.
Then
what's next?
They tried. So then they tried to produce a pair of inclined cable stays that connect kind of the main cables of the bridge to the center of the bridge. So basically to try to...
I'm on fire today. My guesses are on.
Basically to try to create some more stiffness in the actual cables. And that doesn't snap, but it also doesn't prevent the bridge from collapsing. So whether or not it was effective remains kind of in question. And they also try to install hydraulic buffers between the lower, basically between the tower and the actual deck of the bridge, and so that they can basically counteract the oscillation. So they can create basically a damping effect to prevent the kind of harmonic building of these oscillations, right?
So back in the day, when we talk about hydraulics, are they literally just popping in springs?
Yeah, basically. They are popping in. Well, so it's actually a damper, which is an important part of any sprung system. So what a damper, in this case, a hydraulic damper, basically all that it is it's a piston, and you've basically got maybe one of the only things that's not a spring.
Oh.
Which,
The
yes,
cursive
which
language.
is the cursed language, the forbidden arts of not spring. But it's a fluid, right? So it's a non-compressible
incompressible.
fluid, and basically what you do is you have a piston with fluid on both sides, and you have a plate with holes drilled in it.
Okay.
And basically what that means is that there is a lot of resistance to the motion. So all that you're trying to do with that effectively is create, basically as the spring, in this case the bridge, tries to compress that hydraulic damper, the fluid has to travel through these tiny little holes in the plate in order to let the piston come down.
That's pretty clever.
And so the piston does come down, but it comes down slowly. And then the reverse is true. So when the spring tries to pull it back up, again, it slows it down because the fluid has to go through these small openings. And that's the basic principle of a damper. And obviously that's very important in a lot of different systems. You can find, they're called shock absorbers sometimes. You can find them on cars.
I think I've seen those on
You can find
trains.
them on bridges. You can find them on trains. They're everywhere. They're very, very common.
Looks like a little cylinder with some waves in it.
Yeah, pretty much. Well, we're usually from the outside, you can't see anything. It looks it's just a cylinder with another cylinder inside of it, so it can move.
That's pretty clever design. It's so simple because, like you
It
said,
is.
fluids are incompressible, which is something I learned when we were talking about the name for this podcast. And
It is.
yeah, it's like you're using that what would be a fault to your advantage here. Did that work?
Yeah. Well, Derek, let me ask you something about about shocks, right? What's a really good way to destroy a shock?
To get down on it.
Well, you could get down on it. That's true. And what does getting down on it make the shock do?
Well, I'm guessing metal has, I don't know the best word for it, memory, right? So if you compress something for a long time, it may have the tendency, instead of bouncing back to its original form, staying compressed. So I guess if you had the same kind of wind, I know that sounds really dumb, but if the bridge is, for example, forced down for a long time, you might not get the same effect over time.
That's potentially true. So you could have fatigue loading, but specifically in the damper, right? So this is this oil-filled
Well, if it
hydraulic
cracks,
cylinder.
you lose your fluid.
Yes.
And how do you know that it's
So-
cracked?
Yeah, the really critical part of a damper is that the fluid all stays inside the damper. And so when they sandblast the bridge,
Oh, this is something you do.
before they paint it,
Oh,
they
wait,
destroy-
before they even start using it, they screwed it?
yeah.
Oh my
So
god.
So they sandblast the bridge in order to paint it, which is also very important. Bridges really have to be painted regularly in order to prevent corrosion from destroying them. But the sandblasting destroys the seals on the hydraulic cylinder.
You're kidding me.
So all the fluid then, when the bridge actually starts oscillating, just escapes. And all that non-compressibility is lost.
Huh. So it is a spring, just not by design.
So it is a spring, just not by design. So then...
God, that's so unfortunate.
Yeah, so then basically here's what happens, right? The Washington State Toll Bridge Authority hires this professor, Frederick Burt Farquharson. Oh boy. And he's an engineer at the University of Washington, and they're basically like, hey, this is the problem we're having. The wind is causing the bridge to oscillate. What can we do about it? So Professor Frederick, he builds a wind tunnel and he builds a scale model of the bridge. And he does a bunch of scale testing and stuff like this. And they basically conclude that there's a couple things that they can do to fix this.
All right.
First thing, drill holes in the lateral girders to allow airflow to circulate or through the structure, basically, to reduce the amount of force that's basically, because you've got this 8-foot wall of steel.
Right, just make it a net.
So if you make it, so if you make it a net, you keep a lot of the structural rigidity and strength, but the wind can pass through it.
That won't destroy the beam, right?
And basically
they know where to drill.
You do have to be a little bit careful about it, but you can drill a lot of holes in a steel plate before you lose the strength of it.
Okay.
Or they can basically create these aerodynamic fairings on the deck, which you were talking about, in order to basically prevent the aerodynamic, or to shape the aerodynamic forces specifically so that the bridge can accommodate them. So it acts in the strength of the bridge, which basically direct it into the cables.
Well, I got a question, Jim. Because we wouldn't be talking about it if everything went right. Which one's cheaper?
Well, so there's a couple reasons that they decided what they decided. And then there's a couple reasons why it didn't matter. So they decide, okay, we don't want to drill a bunch of holes into the bridge because we can't undrill those holes, right? Like if it doesn't work, or we can't undrill those holes. So, all right, let's start looking at this fairing idea. So the studies about this conclude on November the 2nd, 1940. Unfortunately, the bridge collapses on November the 7th.
No, what?
So they didn't have time to implement any of this.
Can you imagine, stacks paper on desk, slaps back. We did some good work.
We figured it out.
We saved the city. Oh, no.
We saved the day. And then 5 days later, the bridge goes down.
You maybe go on vacation. You're just like, all that hard work's finally going to pay off. We can send it to the, budgeting department. Nope.
I'd be mad.
Can you imagine? Oh, Frederick. My heart's with you.
Indeed. So on November the 7th, 1940, at about 11 a.m., the bridge collapses. And what this is caused by is wind. So the wind is really, really strong that day. And there's actually an editor for the newspaper, the News Tribune. He is the last person to drive across the bridge. And here's what he says in his words. Around me, I could hear concrete cracking. I started back to the car to get the dog, but was thrown before I could reach it. The car itself began to slide from side to side on the roadway. I decided the bridge was breaking up, and my only hope was to get back to shore. On hands and knees, most of the time, I crawled 500 yards or more to the towers. My breath was coming in gasps. My knees were raw and bleeding, my hands bruised and swollen from gripping the concrete curb. Towards the last, I risked rising to my feet and running a few yards at a time. Safely back at the toll plaza, I saw the bridge collapse in its final collapse, and my plunge... Excuse me. I saw the bridge in its final collapse and saw my car plunge into the Narrows.
Man, I'm talking about minutes.
Yeah.
If he didn't choose to start going when he did, that would have been him.
That would have been him.
Wild.
So, unfortunately, rest in peace, Tubby. The Cocker Spaniel. That's the name of the dog.
Oh, the pup?
Yeah,
Throw
so the dog
whole episode away,
died.
man.
I know. Anyways,
gosh,
so,
damn, rip Tubby. That's so sad. That's sadder than the bridge.
Yeah, it is very.
He didn't know. It's not his fault.
So so apparently, I kind of blame it on the dog, actually, because, and here's why. Here's the only reason why, right?
I'm dying.
So basically. Here's why this is so silly. So basically, this guy, the newspaper guy, Leonard Coatsworth, this isn't even his dog, right?
What?
So it's actually his daughter's dog.
Oh.
It's his daughter's dog. And Coatsworth was trying to give this dog back to his daughter, who lived in Tacoma, and that's why he was going there. He tries to get this dog out of the car, but the dog won't come. Basically, Tubby is too scared, and so he stays in the car. And he bites, he tries to just pull him out, and he bites Coatsworth. So
I can't blame
I don't know.
Coatsworth. Like, it's a life or death situation. You have to make hard decisions. It sucks that dogs
I
love to get
know
out of the car. It's like their
they
favorite thing to
do,
do.
but not Tubby. I'm afraid.
Tubby. I guess
So
the dog's
unfortunately,
mind, the
yeah,
safety of the car made more sense. And then
yeah,
obviously
yeah.
Coatsworth is like panicking, so the dog only sees the panic. That's so
Absolutely. Yeah. And
sad.
this actually brings up a really interesting point about like dog training that I just here's a little tangent for you that I learned because one of my COVID rabbit holes was like dog training.
Interesting.
And one of the things is that dogs are actually really good about picking up emotion. So if you are freaking out, so for example, like one of the tricks to train like dogs that are aggressive to other dogs, one of the things that can happen is because it's so like let's say you're walking your dog who's aggressive, and another dog comes down the other side of the street. So if you start tensing up because you're expecting your dog to start going off, your dog will actually feel that, and they'll think that you're being threatened by this other dog that's coming across the way. So then that actually encourages your dog to be aggressive towards that other dog
So
because
the
he now
aggressive
thinks that
dog's
he's
trying to
protected.
protect you, but
Yes.
you're just predicting what the dog's gonna do. That's a what do you call
Yeah,
it? A
it's this
feedback
really
loop.
interesting like feedback loop. Yeah, so all I can really say there is that the relationship between humans and dogs is also a spring.
Everything's a spring, Jim.
It's an emotional
Everything.
spring.
Everything. That's so sad. Rip Tubby,
It
man.
really is. It really is. So Coatsworth, actually, he was received $450 for his car,
I guess cars
which
were
is
like not that expensive, huh? All
yeah,
things
I mean that's the
considered.
equivalent of $9,400 today. And he received $364.40 in reimbursement for the contents of the car, including Tubby.
Tubby's worth more than the car, man.
Just about as much. So, basically,
God.
now the question is like, okay, why did this happen? Because remember, this was this was like a $6 million at the time project, and nobody was killed except for Tubby. So that's a blessing.
Yeah, I guess
Um,
that's good. That's a pretty reasonable death count, but we won't forget you, Tubby, even into the
yeah,
2020s.
and there's actually a film of the collapse.
Is there really?
There is, because and it's kind of a grainy film, but it's
Still.
quite wild. I'll send it to you
Why
here.
were they recording?
Because it was cool.
Oh, they knew it was gonna go down?
Well, I guess they didn't know it was going to go down, but like, I mean, I guess at a certain point, once the concrete starts cracking, it's a news story.
Barbara, get the camera!
Exactly.
And then that takes 20 minutes.
Yeah, yeah. Well, but that's true. Basically, there's this question of like, okay, what's going on here? Um, and they're trying to like, oh gosh, so they're trying to collect like the insurance money, and one of the insurance companies has been basically like defrauding the insurance money, and so they can't get the insurance money, and that's like a whole thing.
What? An insurance company corrupt and not willing to pay out the thing you give them money for every... Come on, Jim. Listen, this is a
Yep.
non-fiction podcast. Let's get real.
Let's get real. So this actually sends kind of a ripple effect through a lot of other bridges that are insured by that company, and then they basically sue the crap out of them and they get their money. But anyway,
Do it for Tubby
there's
Insurance Company, you sons of bitches.
there's an investigation into the cause of the collapse. Ultimately, I mean, it really comes down to a twisting failure because what happens because the bridge is relatively narrow and it's relatively shallow, what ends up happening is that the girders basically create eddy currents of air under the bridge. And so it creates this twisting effect. So the bridge starts to twist and up and down at the same time. And this is the first instance of this particular twisting failure coming into play because up to this point, the bridges have not really been long enough and narrow enough to see this type of failure.
Oh, so real quick, just for my sake, and probably some of the listeners, an eddy current, what is that? Is that just like
Okay.
vortexing?
Yes, it's exactly that. So basically, the Tacoma Narrows, as we said previously, it's basically an 8-foot solid wall of steel. right? And one of the solutions was to drill holes into it, right? And they didn't do that, but the reason that that's a problem is because basically you have the wall of the bridge, and as the wind is hitting that wall, there's basically the bottom and top edges create these shear lines, where basically if you imagine the wind coming over the top of that, there is you basically have like the high velocity air coming over the top,
Mm-hmm.
and then nothing under, like right behind that panel, you've got nothing.
So you have an
And
area
so
of
that
low
actually,
pressure.
you have an area of low pressure, which creates basically the air is going to want to fill that, and it creates this eddy, like vortex, basically.
Huh.
And that causes like really weird forces to start happening. And so basically what you have is basically as that vortex is formed, it creates a twist. And then the top angle is there, or the top bridge, basically, or the top plate, the top edge of that windward plate basically has now a even sharper angle to create a deeper vortex. And then it switches back the other way. And so you have this twisting motion.
Hmm.
And so it basically, again, it creates even more, what it's actually called is aeroelastic flutter. That's the technical name for this.
Aeroelastic flutter. That sounds sick.
Yep. And, sometimes you can feel this, like, so if, for example, if you're driving and you have if you have like a window, like partially up, right? And sometimes you'll hear this like vibrating noise in the car, like it'll kind of hurt your eardrums because it's like, blah, 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 blah. Have you ever heard that before?
Yeah. Like it's almost, I don't know if that's the right term. It starts sounding like a resonant frequency problem. Like
That's
right
exactly
before
what
a
it
glass
is.
breaks.
That's exactly what it is. Because basically what's happening is that window is actually unsupported, relatively unsupported.
That's true.
And
it's just supported at the bottom and at the edges, right?
yeah. And so what happens is as the air coming outside the car basically, passes by your window, you have this low pressure area within the car because, well, actually, technically speaking, the area of low pressure is the high velocity stream of air. But you have a separation angle, basically, where the wind starts to form an eddy current. And that hits the glass, and then it kind of shakes it back and forth. And so that same effect happens in the bridge. And usually, in your car, it's annoying and maybe a little bit painful for the eardrums because of that pressure change. But ultimately, it's not a catastrophic failure. But in something like a bridge where you have these resonant, it's basically because it's a self-sustaining oscillation, and there's no damping capabilities on this bridge because they were destroyed. It creates larger and larger amplitudes. And aerodynamic flutter has actually led to a number of different catastrophic failures, including in various airline flights and early and early airliners, which I think would also be an interesting episode. But also, obviously, this bridge.
This is why, I mean, I know it's a lot more to it, but my brain works in simple examples that I can like find in the real world. Is this like partially the reason why airplane windows are round? So that they're more stable structurally?
No, not necessarily. I think the reason that aircraft windows are round is really more to do with stress concentrators. So because the hull of the aircraft is a structural member, you basically don't want sharp corners.
Makes sense.
Because sharp corners create stress risers. So those are places where you can have accentuated fatigue loading and stuff like that. And a lot of aircraft are made out of aluminum because of the light weight, but aluminum is also relatively prone to fatigue cracking. So I think that's probably why most aircraft windows are round, but I don't really, to be quite honest, I don't know the answer to that.
We'll probably talk about it at some point, to be fair. But it's interesting, like even, we're getting vortexing on a bridge. If Professor Frederick's project was greenlit a week earlier, could have been prevented, or at least noticed earlier.
Well, I think part of the toughness, right? Part of the tough thing is, they really would have had to have some damping quickly enough to, to be able to prevent, like, in order to prevent this collapse, they would have had to have installed a fix,
Right. I guess,
you
yeah.
know, before November 7th. So that's the tough thing. And yeah, one of the things that this kind of leads to is this realization of, like, maybe we should do the scale model testing before we start looking at these problems with the real thing.
The hindsight is 2020 with that one. Because, like, if you were to propose it first, it's just like, why, there's nothing wrong with my bridge. There's nothing wrong with my bridge. But, so I have a question. Those dampeners you were talking about, where they sandblasted, fluid came out, did they know that?
So I don't think the fluid would have come out immediately, right?
Oh, this is a slow leak.
It's a slow leak, and that's all it takes for a hydraulic dampener to fail, is a slow leak of fluid.
You're adding pressure. It's going to move the fluid out when you're not looking, while the bridge is in use.
Exactly. And because, I mean, the bridge has a relatively short lifespan. It basically, it opens, it opens to traffic July 1st, and then it collapses November 7th. So it's like, what, 6 months?
Maybe. They got nothing out of it.
Yeah. So, I mean, that even for a regularly inspected bridge, like, that's a pretty short amount of time to be able to notice that type of failure. And certainly today's rigors of bridge inspection are much more thorough than at this time.
It's interesting, like, something as simple as a scale model, which is so ingrained in, like, modern engineering, especially when you're talking about, like, vehicles or, like, structures like this, buildings, for example. And, they put them on shake plates to, like, test how it would be in a, like, earthquake area. But I just thought that was a part of engineering since the dawn of time. I don't know why I thought it'd make small one first. I didn't know that wasn't common practice.
No. Well, I mean, and I don't think it was, because otherwise, you'd think to have seen this. So I've thrown down a couple of links to some different animations, because it's actually quite interesting. And maybe this will be in the YouTube video. I don't want to plug the YouTube too hard, but this is kind of difficult to explain over audio podcast. But basically, what you can see here is the oscillation. And so you'll see, like, the high velocity air and the pressure zones basically creating this fishtailing effect where you kind of have this flapping. And that ultimately is what causes the bridge to fail.
Oh, and it's really interesting to visualize it here, because you can see the, like, what you said, the amplitudes kind of combining in a way. You see the like, oh, it's twisting a little bit more to the left than right, and then it gets a little bit worse, more and more, and makes this feedback loop that, as we all know, ends in one way, either release or failure.
Yeah, and that's caused by basically, like, this vortex shedding that's happening. So it's really interesting from, like, kind of a scientific phenomenon.
I think this is ironically, the shortest project, because usually when we're talking about bridges, it's up for 5 years, people kind of wipe their hands of it by then, but this is in the first year of use, and on top of all of that, it was no human casualties. I'm going to count Tubby as one.
One casualty.
Which is pretty low, all things considered, for a project of this scale. Like, what are the odds one person was on the bridge at that specific time?
Yeah, well, I imagine part of it is, like, the bridge is moving a lot.
Oh, so people were just like, nah, man.
Yeah, people are like, that ain't me.
We're going to Tacoma tomorrow, screw that noise.
Exactly. But yeah, I mean, what ends up happening is there's a lot of research that goes into wind-driven resonance. Excuse me. And the bridge doesn't get rebuilt until after World War II.
Well, I guess they got other things to build. They need that steel for other things.
Yeah, they scrap the steel to basically make
You're
stuff
a bomber
for
now.
World War II. Yeah.
Dang. It's interesting
But
when you
yeah,
listening to you talk about these engineering failures, and I guess the audience with us gets 9, right? I've gotten years of this from Jim, just us, over a couple drinks, just talking about things, and then it deviates, and you guys are seeing our tangents. It's interesting. You can think about this Tacoma Bridge disaster and look at it in your daily life and see things at a much smaller scale that pretty much do the same thing. For example, I keep watching the flag for the mailbox that like pops up when you want like mail to be sent. I've watched this thing get ripped off like 4 times in the last 5 years. And it never occurred to me once to drill holes in it. And that would just solve the problem.
In theory.
I just keep replacing it.
Aerodynamics are like they're a very complicated subject. So
knock, knock, open up the door. Kasha, we need you.
She would actually be a phenomenal resource to talk about this. Because she trained specifically as an aeronautics engineer. So yeah, this is like directly in her wheelhouse. Really, my mechanical engineering degree didn't cover a whole lot of aerodynamics. It's a very complicated. I mean, you could very easily get a PhD just talking about aerodynamics.
Hey, if it makes you feel any better, my biology degree involved 0 aerodynamics. So cool.
That's fair. But really, the big lesson, the big takeaway from this is really where the widespread testing in wind tunnels becomes widespread and eventually made mandatory for these large structures. And in addition, the Bronx Whitestone Bridge in New York, which is a similar design, was reinforced after the collapse. They added additional big 14-foot steel trusses on both sides of the deck in order to prevent it from oscillating.
Brilliant. What do you call it?
Really great.
Mitigating reactively. Not reactively, proactively.
Exactly. Mitigating proactively. And then in 2003, they actually took those trusses off and replaced them with aerodynamic fairings to reduce the oscillation.
Better every day. That's what I'm talking about. New York, let's go.
Absolutely. And here's a man by the name of Othmar Aman's kind of thoughts on this. The Tacoma Narrows Bridge failure has given us invaluable information. It has shown that every new structure that projects into new fields of magnitude involves new problems, for the solution of which neither theory nor practical experience furnish an adequate guide. It is then that we must rely largely on judgment, and if, as a result, errors or failures occur, we must accept them as a price for human progress. End quote.
That's a powerful statement.
It's a powerful statement. And to a large degree, I mean, it's true, right? And obviously we always want to try to mitigate any risk, especially to human life, of these projects. But to a certain extent, this has been proven out time and again. Whenever you're building something that's truly novel, you're going to have problems along the way.
Yeah, you can't go to the moon without crashing a couple rockets. It's unfortunate. It's sad that sometimes, we see things like simple things that just get in our way. And then like you see this wind. I mean, I know wind is not a simple thing engineering wise, but it's
a very common thing.
Exactly. It's one of the last things you'd think of. Like you're thinking of the weight, you're thinking of the oscillation, you're thinking of, like you said, the tension and all of these other variables. But is this the environmental episode you were referring to a few episodes ago?
This is exactly that.
Man,
because it's really, this bridge was solely destroyed by the wind and its design.
God just said, nah, man, next time.
Absolutely. So that is the Tacoma Narrows Suspension Bridge.
Man, I mean, that's a good place to stop. I
think so.
I think that guy, the quote that you gave, wrapped it up better than I ever could.
It's a pretty good, I mean, yeah, it's just there's a lot of wisdom in that statement. And I think really what it comes down to is, how can we protect ourselves and the people around us from that failure, right? Like that's ultimately, I think if you look at a lot of engineering post 1940, a lot of what is done to mitigate the risk to human life.
Right.
Right. So like now we're testing these in wind tunnels. We're building scale models. In fact, like the Golden Gate Bridge, there's this whole like scale model, but basically they built like an enormous, fully sized scale model of the entire like San Francisco Bay. Yeah. So the Army Corps of Engineer actually created a hydraulic scale model of the San Francisco Bay, basically to test infrastructure in the San Francisco Bay region before they built it.
That seems smart. I guess like past actually, oh, does it fit here? You could do some cool things about traffic and all other sorts of infrastructure. Like where's the sewage going to go? You can actually get a physical model. Hey, if there was flooding in this area, what does that look like? Where does it spill to?
Yeah, absolutely, and it's really cool. Here, I'll just drop the I'll drop the link to the San Francisco. It's the Army Corps of Engineers Bay model.
Bay Area,
Um,
area.
I'll drop that in. Maybe we can put that in the show notes as a bit of a tangent, but it's really quite incredible.
Well, that's massive.
Yeah, it's huge. It's like 2 acres. Like it's huge.
Well, before we get too far off, we should wrap there because I think we're about
Yeah.
at time.
We're at time.
Jim, you got anything to plug?
I don't think so today. I'd plug the Whiskey Grail, except that we're getting kicked in the butt right now for production and the Christmas season. So buy a Whiskey Grail, but we might not get it to you for a little while.
So yeah, we've passed the point of you're getting it for Christmas, but think about that delicious post-winter whiskey that you could be drinking out of your brand new, I'm talking oak-made whiskey roll. I just got a new one and it rocks. It made one of my really crappy scotches actually palatable, which is crazy to think about because I really did not think I'd get through the bottle.
Well, I'm glad it has made your drinking experience better, Derek, and thank you so much for your support. Shout us out on Twitter, the company now known as X. Also, we have Instagram. Check us out on our YouTube for some visuals. Derek's been kicking butt with the visuals on the YouTube lately, so check that out.
Yeah, this one's going to be a little late because I had a life this week, but it'll be out by Monday.
If you've got any comments or want to give us any feedback, please feel free to drop us a like or a comment on our YouTube channel or here on Spotify. Hit us up with those 5-star ratings. That really helps the channel or helps the show out. Let us know what you thought and get in touch with us. We'd love to hear your feedback.
Well, Jim, on that note, let's bounce.
Let's bounce.